Well, this is the Media Lab, so I thought I'd talk about media. But I'm going to talk about a particular kind of media, which is media for thinking in. And I'm going to talk about a particular kind of thinking, which is understanding systems. So as an example of that, say you've got some system out in the world, such as the planets going around the sun. You want to understand what's going on there. So you take some measurements, you look for patterns, you build a theoretical model, and that's the kind of thinking that we call science. It's a very important kind of thinking. But you can also go in the other direction. Instead of going from the system to the theory, you can start from theory and build your own system, like a spacecraft to take you to a planet. And that's the kind of thinking that we call engineering. But either way that you're going, whether you're going from system to a theory or from theory to a system, understanding the system is really at the heart of what you're doing. So both science and engineering, or everywhere in between, a lot of it comes down to understanding systems. And media matter because media are thinking tools, right? The representations that we use of the system are how we think about it. Our representations are how we understand the system and what we understand about it. And so if we want powerful new ways of understanding complex systems, or if we want to build powerful new systems, we need powerful new representations. And we need a powerful new medium in which we can create and work with those representations. So much of the way we work with systems today is derived from pencil and paper, from the pencil and paper medium. Even when we're working on the computer, we're still thinking in pencil and paper. And I think there's an incredible opportunity now to rethink how we think about systems. So in this talk, I'm going to show you a bunch of different examples of different representations of different systems, and to try to kind of give hints as to what this new medium for working with systems might be. These examples are kind of from all over. There's like programming, circuit design, and signal processing, and this and that. If you're not familiar with one of these domains, doesn't matter. You don't need to know any of the technical details. All that matters is the representations. Every idea I show here can be pretty much applied to pretty much any domain. So I'm going to start off with taking a look at a scientific paper. This is a paper on network theory that was published in Nature a little while ago. A very influential paper, basically started an entire field of network theory, and it kind of looks like a paper, right? You've got a lot of words and numbers, and here's a figure, and here's a table, and there's another figure. I'm going to read a little bit to you from this paper, from the introduction, second paragraph where they're kind of setting things up. The networks of interest to us have many vertices with sparse connections, but not so sparse that the graph is in danger of being disconnected. Specifically, we require that n much greater than k much greater than log n much greater than 1, or k much greater than log n guarantees the random graph will be connected. In this regime, we find that L goes as n over 2k much greater than 1, and C goes as 3/4, as P goes to 0, and this is incomprehensible. And this is a very well-written paper. The authors are excellent writers. What we have here is the authors have a very rich picture in their heads, and they're trying to compress that picture to transmit over a very low bandwidth channel, which is this stream of numbers and symbols, right? So it's a very lossy compression, and we've got the reader on the other end trying to decompress this picture into their own head, and it doesn't work very well. So I redesigned this paper, and my redesign looks a little bit like this. So you can see words and pictures very tightly intertwined, a little bit of words, a little bit of pictures. I'll read a little bit to you from this part up here, where they're establishing the algorithm that they used to generate these networks that they study. We start with a ring of n vertices, and here we see a ring of 12 vertices, where each vertex is connected to its k nearest neighbors. Here we see k equals 4 connections, like so. Now they're all connected. We choose a vertex and the edge to its nearest neighbor. There's the vertex, there's the edge. With probability p, we reconnect the edge at random. There it is reconnected. We repeat this process moving clockwise around the ring, like so. So instead of just describing the algorithm, it's depicting the state of the system at each step. So this is what you normally would have to construct in your head. Here, the picture in your head is just illustrated. Here they're discussing some relationships. The regular lattice, L grows linearly with n. We see L growing linearly with n. We see C is staying constant. The random network, L grows logarithmically. We see L grow logarithmically. We see C going as a reciprocal relationship. When we read the word logarithmic, we don't have to reconstruct that relationship in our head. You can just see it. So what I'm doing here, it's it's really just a very simple trick. It's to understand the picture that's in the author's head and just reproduce that. So we're showing the state of the system. We're showing the behavior of the system as it goes through this algorithm. In my next example, I'm going to go to a completely different domain, but I'm going to use kind of the same trick. So this next example is an example from circuit design. So here's a circuit that I'm working on, and I'm not done drawing it, so let me finish drawing it. And that. And now the circuit works, although you can't actually see it working. You can't actually see anything. So we kind of have the same problem as with that original paper, is that the system is doing something, and we can't see it doing anything. If you were to build this circuit on a lab bench, you could at least take an oscilloscope and probe around and see what's going on at this node, what's going on that node. So you should at least be able to do that. So here, I'm showing the voltage at that particular node, and it's simulating in real time, and we can see what it's doing. But you still can't understand the system. In order to understand the system, it's not enough to just see one variable, one voltage. You have to see all the voltages. You have to see all the variables. You have to understand what's happening here and here and here and here and here and here. And normally you have to reconstruct that in your head. But if I spread these out a little bit and switch to this representation, now you can see all the voltages across the entire circuit. I can scrub over them. I can see what's going on in this region. I can compare any two. The one that I'm mousing over right now, its shadow is overlaid on all the other plots, so I can compare them. I can adjust anything in the circuit, such as this resistor, turn it up or down, and I see immediately how the behavior changes. So we're a little bit further towards understanding the behavior of the system, but it's still not enough. We're really only seeing half of the behavior now, because in electronics, there's both voltage and current. In order to understand what the system's doing, you have to understand both of these things. So what I'm going to do is I'm going to replace each of these components here, such as this resistor, with a plot of the current going through that resistor. So right now, each of those blue blocks represents a component. This one right here is a resistor. This one's a capacitor. You can see what it is because they have a little badge. But instead of just being a dead schematic symbol, now it represents behavior. And so I can now, at a glance, see the entire behavior across the entire system, all the voltages, all the currents, compare all of them. I can change anything about the system and see immediately how the behavior changes in response. Now, this representation here has all the same structural information as this. You still have the resistor hooked up to the capacitor, hooked up to the transistor. The difference is now, instead of just being made out of these squiggly symbols that were designed for pencil and paper, now it's made out of live data where you can see what the system's doing. So this is a paper about network theory. This is an engineering design using the same trick, which is just showing the behavior of the system. So with those two examples in mind, I want to step back a bit and kind of talk a little more abstractly about what's going on here. One way I like to frame this work is with a quote by Richard Hamming. Hamming was one of the old Bell Labs guys, did world-class research in all sorts of fields, thought a lot about how people think and how people do research. And in his paper, The Unreasonable Effectiveness of Mathematics, he said this: just as there are odors that dogs can smell and we cannot, as well as sounds that dogs can hear and we cannot, so too there are wavelengths of light we cannot see and flavors we cannot taste. Why then, given our brains wired the way they are, does the remark, "perhaps there are thoughts we can't think," surprise you? Evolution so far may have blocked us from being able to think in some directions. There could be unthinkable thoughts. Now, Hamming was a brilliant guy, and he thought a lot about thinking. And so what I think is really interesting about this passage is that, to me, there's a really obvious response where Hamming didn't go, which is to say, these sounds that we can't hear and this light that we can't see, how do we even know about these things in the first place? Well, we build tools. We build tools that adapt these things that are outside of our senses to our human bodies, to our human senses. So we can't hear ultrasonic sound, but you hook a microphone up to an oscilloscope, and there it is. You're seeing that sound with your plain old monkey eyes, right? We can't see cells and we can't see galaxies, but we build microscopes and telescopes, and these tools adapt the world to our human bodies, to our human senses. right? So when Hamming says there could be unthinkable thoughts, we have to take that as yes, but we build tools that adapt these unthinkable thoughts to the way that our minds work and allow us to think these thoughts that were previously unthinkable. And I'll give you a couple examples of these kind of adapting tools. Probably the greatest one in the history of humanity is writing. Writing made thought visible. Writing allowed us to think about thinking. Thinking and speech used to be this really fleeting thing. Writing allowed us to capture it, to study it, and it's widely considered that the invention of writing was the invention of reason. It was the invention of rational thinking, when we had this new representation where we could capture thought and think about it explicitly. And the thing about having a literate culture is that if you've grown up with literacy, you're now able to think in this much more powerful way. Even if you're not writing at that very moment, you're still able to think literately. That was Marshall McLuhan's deal, right? You introduce a medium into society, and it changes the thought patterns of the society. So writing was this really powerful tool for allowing us to think thoughts that were previously unthinkable. Another really great one was mathematical notation. So I'm going to show you a math problem that was addressed by the great mathematician Al-Khwarizmi around the year 900. He wrote, "What is a square which, when taken with 10 of its roots, will give a sum total of 39? Now, the roots before us in the problem are 10, therefore take 5, which multiplies itself gives 25, and so on and so on. And it would be another 800 years before we'd be able to write that same problem in this form." So there's a structure that's visible in that bottom form that's invisible, it's hidden in the recipe. And once you take that concept and make it visible, now you're able to think explicitly about it, you're able to develop means of manipulating it. And the invention of this notation is widely considered to be the birth of modern mathematics. One reason being that once you have it in that bottom form, you can start to think, well, what if x isn't a number? What if x is a velocity or a matrix or a member of some abstract group? And I think it's really interesting that the birth of modern mathematics is considered to be not any particular mathematical concept, but a user interface, right? So when I'm talking about thinking unthinkable thoughts, this is the sort of thing I have in mind. These representations that make concepts visible that used to be invisible and allow us to think explicitly about them, allow our minds to go in directions that couldn't go before. Now, in the same way that if you're going to build a microscope, it probably helps to know a little bit about optics, know how the eye works. If you're going to build a thinking tool, it probably helps to have some idea of how people think about things. And one simple framework that I like is one I got from Jerome Bruner, who adapted it from Piaget, and he talked about these 3 different mentalities, these 3 different ways that people have of thinking about things, which he called the inactive, the iconic, and the symbolic. And in modern UI terms, they might be called interactive, visual, and symbolic. So interactive is thinking by doing, by actively exploring, performing, thinking with your hands, being a body in space, all that. The second channel, visual channel, is thinking by seeing, especially seeing many things in parallel, being able to make comparisons, being able to recognize shapes, thinking with analogies. The third channel, symbolic, is thinking with language, step-by-step logical reasoning, all that. One great example of that first channel, interactive, is the discovery of the structure of DNA by Watson and Crick. So Watson and Crick had some data from Rosalind Franklin's X-ray experiments and other kind of chemical knowledge, but the way that they were able to figure out the structure of that molecule is they went down to the machine shop. And they built these physical models out of brass and wire, and they went up to their office and tried to fit them together. And they were ridiculed by their colleagues. Their colleagues are like, hey, it's Watson and Crick playing with their toys again. And then, 10 years later, Watson and Crick are like, yeah, it's Watson and Crick playing with our Nobel Prizes again, right? So the structure of DNA was unthinkable. Like, literally, nobody could think of it. They were able to think this thought by moving it from the symbolic channel to the interactive channel where they could think with their hands. And nowadays, of course, all chemistry students play with physical models. It's just totally standard. A great example of thinking in that second channel, the visual channel. 1786, William Playfair was writing a book about economic trade balances in the European countries, and his book was full of these tables of numbers, so many exports from Finland, next page, so many exports from Germany or whatever. And he had a thought, which was, what would make these numbers easier to understand is if I drew a map of numbers. And so he drew this, which was the first time anybody had plotted data. This was the first data graphic. He filled his book with these things and invented the field of statistical graphics. So again, this was this kind of channel switch where he took something that had been purely symbolic, a table of numbers is about as symbolic as you can get, and turned it into something that could be understood in an entirely new way. So this sort of channel switching is basically what I'm trying to do here. The behavior of this system can only be understood symbolically. You kind of have to logically reason, like, here's what a capacitor does, here's what a resistor does, step-by-step simulate in your head. When we move to this representation, the structure of the system is still symbolic. We still have a symbol for the capacitor, a symbol for the resistor. The behavior of the system can now be understood visually. And by visual, I don't just mean like seeing a plot, but seeing many plots in parallel, being able to recognize shapes, being able to compare them, that kind of thing. So we have the symbolic, we have the visual, and then we also have this interactive channel where we can adjust the structure of the system and see how the behavior responds. So we can have hypotheses and test them out, play out what-if scenarios, build associations between how we're interactively probing the system and how the behavior is responding. So we're kind of firing on all three cylinders here. Instead of this just being a big pile of symbols, we've got the symbolic, we've got the visual, and we've got the interactive. And they're all kind of working together and reinforcing each other. So in the next example, I want to show not just having multiple representations, but having different representations for the same behavior, being able to look at the same behavior in different ways. So this is an example from signal processing. This is a digital filter. Again, don't worry if you don't know what that is. This is just a system. Here are some equations that describe how it works, and here is one way of representing what the system is doing. It's a frequency response. And the system has two parameters, the cutoff and the Q. And I can grab this knob and drag left and right to adjust one, drag up and down to adjust the other. You'll notice there's something else happening when I'm dragging this around. So if you look up here, there's this coefficient kf that's being multiplied. And in this representation, I have no idea what kf is. Like, is it near 0? Is it near 1? Is it near 100? Is it negative? I have no idea what the range of this number is. As I'm interacting, you'll see that number changes to a concrete coefficient. And now I can get a sense of exactly what coefficients I'm dealing with. Over here, we're seeing numbers appearing in the equation, where before there were expressions. So we can get a sense of the coefficients there. Up here, we're seeing a step response, a time domain response. And below, we're seeing the poles in the z-plane. That's a frequency domain thing, like the Laplace transform. And then over here, we're seeing how the Fourier transform is responding. So these are 5 different ways of looking at the behavior of the system. And as I'm interacting, we're seeing all 5 of them responding at once. We're seeing these 5 different perspectives on the system, each with its own insights, and we're seeing how they all dance together as I change these parameters. And what this does is this allows you to build up associations in your mind. So when you adjust the parameter, you see, okay, the poles are moving this way, which is making the oscillation go in this way and making the peak in the Fourier transform go this way. You see all these representations changing together. You build associations between them. And the idea is that that ultimately leads to what we call intuition. The idea that there's some desired response I want, and I kind of know how to get there because I've seen when this happens, that also happens, that also happens. You've seen the system from so many different angles that you can feel your way around it. This is a very different way of thinking than the traditional analytic, write a whole bunch of pages of grungy equations and come out with the answer way of thinking. So, we need to see the behavior of the system. We need to see the entire behavior across the entire system, all the variables at once. We need to be able to interact with the system, see how the behavior changes. We need multiple representations of the behavior to see it from different perspectives and different angles. Something else that we need is to be able to interact with the behavior. All I've done so far, and what I'm doing here, is interacting with the structure of the system. I'm changing parameters, and then we're just looking at the behavior. But you can do more than look at the behavior. You can also work with the behavior. So in this next example, what I have here is an environment for working with difference equations. And again, don't worry too much about what that means, but here I'm defining a variable called a, and I can set it to a constant, and as I move it up and down, you can see that we have this kind of flat line plot here because it's constant. But I can also say that at each step, we're going to subtract a little bit off of a. I'm going to set the initial value here, and then you can see that each step of time, we're subtracting a little bit off, and we get this ramp going down, and I can change that constant and get a different slope ramp. But something else that's really interesting to do is say on each step, instead of subtracting a constant, I'm going to subtract a little bit from some other variable, which I'm going to call b. And then b, each step, I'm going to add a little bit of that a. Let me connect these two so they're always the same. And what we get is this kind of recursive relationship where they end up oscillating. So here's two variables I made called a and b, and they turn into this sine oscillator. Maybe I'll define a variable c, which when a is positive, give me a 1. If a is negative, give me a negative 1. And now we've turned it into a square wave. And then integrate that square wave. And when you integrate a square wave, you get a triangle wave. So taking this behavior and then transforming it in different ways, maybe bring out relationships that are interesting. So far, I've mostly just been working over here on the structure of the system, but I can also work over on the behavior. So let's say I want to know how big this period is. What's the period of the sine wave? Well, I can just click and drag over a region and measure it. So I dragged over that region. I can see that it's about 68 samples wide. And you're also seeing something over here, which is saying the mean is 0, which makes sense if it's a full period. But I can also look at the max or the min, or I can define my own reductions if I want to know root mean squared or whatever. So another way of looking at it, selecting regions and then running reductions over them. Now, this period is 68 samples wide, but then as I change this, the period is also changing, and this selection is kind of going out of sync, so I'd have to select it again, and then I want to know what it is for that, so I have to select it again, and that gets kind of tedious. I'd like to know how the period changes when I change this coefficient here. So what I can do is over here I have a search field. And in search field, I can put in any condition, such as show me everywhere where a is negative. And now I've got these regions I can click on where a is negative. It found all the places where a was negative. And I can search for anything. I can find where a is less than b. Or I can find where a at time n plus 1 is greater than a at n. Now it's found all the rising slopes, right? So what I'm doing here is normally called solving an equation, solving the systems. But here it's treated as searching, which is a very different way of thinking about it. So I want that period, so I can just kind of select from one to the other. And now it's selected over a full period, and I can see that it's 82 samples wide. As I change this coefficient, I see that number is changing. But it's not really enough to just look at that number, the width of that. I want to see how that width changes as I'm changing this coefficient here. So all I need to do is draw a line from one to the other. And now it's plotting one against the other. So this is a plot of, as we vary that coefficient in the equations, it's measuring the width and plotting it. So every point on this plot corresponds to a particular system. Every point on this plot corresponds to a particular set of coefficients here, which means that the plot as a whole is not about any particular system, but an entire family of systems. So we've abstracted over that coefficient, and we're looking at an entire family of systems, comparing them. In this case, this kind of looks like a reciprocal type relationship, a 1 over x type thing. And so 1 over the period is frequency, so maybe we should be looking at frequency instead. So I'm going to define a new variable here. I need some sample rate, so say 48 kilohertz divided by n. And so here's the sample width, and now here's the frequency of the sine wave. And I can plot versus that, and we can see this has kind of a linear relationship. So we need to see the behavior of the system. We need to see the entire behavior across the entire system, all variables at once. We need to interact with the system, see how the behavior changes. We need to be able to see multiple representations of the behavior. And we need to not just see the behavior, but be able to interact with it, to be able to measure it, reduce it, transform it, search it, whatever makes sense for this particular system. And we need to be able to abstract over individual systems and look at families of systems, compare between them. Now, the next example I'm going to show you is about having multiple representations linked together. And this is a programming example, actually. So what I'm showing here is a 2D vector graphics engine. This was written by Dan Amling, who's one of Alan Kay's researchers. And it's remarkable because it does everything that a normal 2D graphics engine like Quartz or Cairo does, except Quartz or Cairo are like millions of lines of code, and this is 500 lines of code. That's the entire code base right there. And Dan was able to do this because he invented a language called Nile, in which the sorts of operations he wanted to do could be expressed very compactly. This is an example of Nile code, and the language is really beautiful. The algorithms are expressed very elegantly in the language, and they're very elegant algorithms, and you can read the code and have no idea what's going on because you can't see the behavior of the system. So working with Dan, I made it an environment for exploring Nile code, and I'll give you a couple examples. This first one is kind of a toy program in Nile, and Nile it's kind of like the Unix pipeline. It's a pipeline language. You put in data, and then a process runs on it and feeds data to the next process, and down the pipeline. So what you see here, we're putting 5 points into the pipeline, and you see 4 points up there because the first and the last one are duplicated. And then those 5 points go into this process called make polygon that outputs 4 Beziers, which goes into this process and that process and down the chain. And so over here, you're seeing a picture, a visual representation of what's in that pipe. And then over here, you're actually seeing the source code of the process because Nile is so compact that the source code for a process can normally just be stuck on the side like a caption. So what you're seeing at each stage is the data at that stage in the pipeline. And if I go up here to the initial input, you'll notice that as I point to any of these initial points, you're seeing Beziers highlighted in black down the pipeline. So what you're seeing is this point went into the next process, and out came this Bezier, and then what happened to that Bezier? Well, it got rounded, it got transformed. You're chasing a particular piece of data all the way through the pipeline. And of course, I can grab the initial input and adjust it, and you can see how the data is changing all the way through the pipeline. But I can also do this in the middle. So if I point to this Bezier path, it's showing not just where that data went, but where it came from as well. So you're seeing the entire history of that particular object, both past and future. So this is an example of representations that are linked together, where you point to part of one representation and all the corresponding parts of other representations are highlighted, bringing them all together. So that was kind of a toy program in Nile. What you see here is the actual rasterization texturing pipeline that they use in their system. The rasterizer looks like that, and the texturing looks like that. You put in Beziers, and out comes pixels at the end. You don't have to follow this in detail, but what's really interesting is that you can kind of tell what the system's doing just by going down and looking at the pictures and kind of even ignoring the code. You can just see, like, this data turned into that data, that turned into that data. You'll notice that there's different types of representations for different types of data. So this process right here, for example, outputs a stream of real numbers. So what's a good way of representing a stream of real numbers? Well, we'll just try a bar chart. So the environment tries to pick a visualization that makes sense for the particular type of data. So for the final example, I'd like to address the question of how all these representations come to be in the first place. If you want a medium for working with these representations, the question of how you create them is pretty central. The thing about visualizations is that they're visual. We understand them visually, that second channel, the visual thinking channel. And so I think it's essential that they be created in the same way, created by thinking visually. And creating a picture visually is just called drawing, right? We've been drawing forever. Since the time of cave paintings, people have been creating pictures by direct manipulation of the picture itself. And before computers, that was kind of the only way to do it, right? So if you were a scientist or engineer, 50 years ago, you had your pad of graph paper, you had your pocket full of pens, and when data came along, you would just draw it. So, for example, say I'm a scientist, I run an experiment, I get some data, I want to understand what's going on, so I say, well, there's a couple of variables I measured which seem to be related, so I'm going to plot one versus the other as a kind of scatter plot here. But the order that these samples was taken also matters, so I'm going to connect them up with a line, And there's something else I measured, which was the width, like the region that these samples are valid. And I'm just going to draw that like so. And it also matters whether these samples cover the entire space or if there's gaps. So I'm going to take a highlighter and kind of fill in the columns that these samples cover. And I can see that there's a gap right here that's not covered by any sample, and a gap over here, and so on. And so there's this wonderful expressiveness and directness in drawing that when you want to see something, you're like, I want to see marginals. I need to see my marginals. You just go, doot, 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 right? And there are your marginals, right? And the downside of this way of working, of course, is that we're producing this all by hand. So that limits how complex it can be, and it's kind of a one-off for that particular data set. So if we get new data, we have to like throw this away and draw a new picture, right? And you have the same problem with computer-based drawing tools like Illustrator. They're one-offs for a particular data set. And so what we've seen is that people have turned away from drawing and have instead turned to writing code that generates pictures and processing or whatever, and working in this very indirect, symbolic, linguistic, non-visual way of creating pictures. So instead, what I'd like to show you is a tool for drawing dynamic pictures, a tool for creating data-driven pictures by direct manipulation of the picture itself. And I'm not going to go into too much detail here because this tool is kind of a talk in itself. The tool I have here, it's like Illustrator. It's a vector drawing tool. I can draw a line, I can draw a shape, and I can scale it, and I can rotate it, and all that. The only thing that's different from Illustrator is that as I do these things, it's recording a series of steps. I drew a line, drew a shape, scaled it, rotated it, and so on. And these steps can be parameterized by data. That rotation, for example, I can hook it up to a parameter. Now, when I change the data, the picture changes. So that's the only magic here, is I have this spreadsheet-like data environment, and I can hook it up to the steps of the picture. So if I have that same situation that I drew here, I've got my data, I want to understand what's going on. Well, maybe I'll start off drawing it as a kind of scatter plot. So I'm going to draw a rectangle over the entire canvas and scale the width by one of the variables and scale the height by the other variable, and make that a guide and draw a little dot at the end. And now I've plotted my first point. I can loop that over all the points, and now we've got this kind of scatter plot. Now I want to draw that line connecting all of the points. So I'm going to draw a line using the line tool from the previous point to the next point. And now I need to move my little marker to keep track of where the previous point was. It goes around, and I've got this path, and I'm going to make it a little bit wider and make it orange. Okay, and now I want those widths, those regions that I was drawing before. So I'm going to draw a line across the canvas, scale it down by that width variable, and just kind of plop it over here on the data point. Draw those little wings that I had before. Now I want that thing I did with a highlighter. I want to see the regions that these are covering. So I'm just going to use the rectangle tool and draw a rectangle whose top is at the top of the canvas and whose bottom is at the bottom of the canvas. And let me get rid of the stroke there and make it orange. So now I can see there's a gap in the samples here, and there's this region here that was overlapped by two samples. Now I'm kind of losing track of what direction this is going, like whether it's the samples were taken in the clockwise or counterclockwise direction. So I think instead of seeing lines between them, I'd rather see arrows. So what I'm going to do is I'm just going to draw an arrowhead, just totally kind of freehanding it here, and plop it over here on the point and rotate it by some amount, which I rotated by whatever the angle of that line was. And so now I've got my arrows kind of chasing around the path. Make it orange. Let's scale it down so it's not so ridiculous. And now the scatterplot dots are just kind of getting in the way. So I'm going to select that and hide it, and so on. And so I drew this picture the same way I would draw it in Illustrator by directly manipulating the canvas. But this is driven by data. So if I have another data set, I drop it in, I get a new picture. I have a new data set, drop it in, I get a new picture. Or if I just go into the data by hand, I can just grab this number and kind of wiggle it around, and you see the picture changing. And just as before, if I wanted to add anything, I want marginals. I just use the line tool and draw a line, and now I've got marginals. Direct manipulation of the picture itself. Thinking geometrically instead of thinking algebraically, thinking visually instead of thinking in language. So this tool can create all of the graphics that you kind of expect from a visualization. You can create dynamic shapes. Yeah. But what's important is that you can kind of follow your own thought process and create pictures that have never been created before, and they're dynamic, they're driven by data. They can be used as representations for systems in the same way of everything I've been talking about so far. So, to sum up, we need to see the behavior of the system. If we want a new medium for working with these systems, for understanding them in powerful new ways, we need to be able to see the behavior of the system. That's what we can do now that we couldn't do on pencil and paper. We need to see the entire state of the system across all the variables all at once, be able to make comparisons, recognize things. We need to be able to adjust the system, see how the behavior responds, immediately see how the behavior responds, make those associations between what we're changing and how the behavior responds. We need multiple representations of the system, looking at the behavior in different ways through different lenses, bringing out different insights, being able to compare them, make associations between these representations. We need to not just see the behavior, but also be able to interact with it by measuring it, searching it, transforming it, whatever makes sense. This idea of being able to interact with the behavior of the system is super important. We're normally over here interacting with the structure of the system, and that becomes the system. So, for example, when you're programming, you're working in code. You're thinking about code, you're interacting with the code, you're staring at the code all the time. The code becomes the program. But code doesn't matter. What matters is what the program is doing. And so we need representations where we're over here on the doing side, we're focusing on the behavior of the system, we're interacting with the behavior of the system, we're staring at the behavior of the behavior of the system becomes what it's all about. We need to be able to abstract over individual systems, see entire families of systems, and be able to compare them. We need multiple representations that are linked together, point to one component, and all the other components are hooked up. We need different representations for different types of data, and most importantly, we need a way of creating these representations that's in line with everything else that I've been talking about, and I think that means drawing these representations, direct manipulation of the picture itself. So, everything that I've shown you so far are hints. These are nibbling at the corners of a big problem, the big problem being, what is this new medium for understanding systems? We need to get away from pencil and paper thinking. Even when you're working on the computer, you're still thinking in pencil and paper. All the techniques we have for working with systems are derived from pencil and paper, especially programming. Programming, you're working in a written language. Written languages were designed for writing. In the bottom right corner here, that's Dijkstra's handwriting. He handwrote everything. He logically reasoned about everything. The idea of visually and interactively exploring the behavior of a system wasn't even on his radar. He probably would have found it repugnant. And that's the legacy that we've inherited. So I think we have this opportunity to reinvent how we think about systems, to create this new medium. And I don't know what that medium is, but if you'd like to help find it, let me know. Thanks.